Welcome to this video. I'm going to do a quick walkthrough of Julia coding and how to get started coding in Julia in hopes that you can use this to springboard into your next skill and get some development in the topics that we talk about in the videos on this channel. The first step is to go to the repository, the GitHub repository for this course. And if you go to problem sets, PS1, ps1.pdf, then you can see the problem set that we're going to walk through the first question of. So key things to be aware of: we need to install some packages, we need to set up GitHub, and then we can start writing code. How do we do the packages? Well, we need to open up Julia on our computer and start working on it. Here's my Julia instance. And if you go here, it says bracket question mark for package help. And what we do is we hit the close bracket symbol, and that's going to open up this package dialog. And then we can do something like add distributions. And that's going to cycle through and might take a minute or two, but eventually it will go through and update that package. So for me, I already had it installed, and so nothing needed to happen. But for you, it might be different. Next, I'll show you how to get started in VS Code. So I'm assuming that you've already downloaded and installed VS Code. You can go File, New Text File to get to what I have here. And then here we can just start typing some of those packages. So if we wanted to start doing this code, we would type the names of these packages. And then if you save this as a .jl file, then that's going to register with VS Code that we're coding in Julia. And then if you've installed the Julia language extension, it's going to appear over here. So I've gone ahead and done that. And now we have that the word using turned purple. And then we see these three circles here. That's the Julia extension. So that's going to be useful for us. If we go back to the problem set, the next step is to create a GitHub account and fork the repository. And the way that we would do that is we would just click on this Fall 2026, go up to the top and click the fork button there. That's going to fork it to your GitHub account. And if we wanted to, we could get VS Code linked to our GitHub account and then clone the repository that we've forked onto our local machine. I'm not going to go through that here. I just want to focus on writing the Julia code for now. So we're back here. And now, if you read the PDF, the first step that we need to do is to set the seed. And the way that we comment in Julia is with the hashtag symbol. So I'm going to type random.seed1234. And then if I go here and push play, it's going to open a terminal that's called the Julia REPL. And it's going to take a little bit of time to warm up. But now we've got our random seed set. So everything looks okay here. Now let's get into the coding. So I'm going to set up my comment blocks. I like to code in a particular way, but there's a lot of equivalent ways of coding. So the first question is to draw uniform random numbers. And in this case, we want it to be uniform minus 5 to 10. So there's a couple ways we can do this. And we want to do a 10 by 7 array. So we can say, we can use the built-in generator with the rand function. Here I'm going to do minus 5 dot plus 15 times rand 10, 7. Or I can use distributions dot JL. And here that would be A is equal to rand uniform minus 5 to 10, 10, 7. So these should give us the same thing. I'm going to have it print out A here and then print out A again. And I'm going to hit this play button and it should show us both. So we can see that, it's not going to be the same because we didn't reset the seed, but it's giving us numbers that are both, everything numbers between negative 5 and 10, which is what we would expect from this uniform distribution. All right, so then we have part B. And pardon me, we want to do a little bit more with drawing a normal distribution of part A and then doing some indexing practice. So now we want to do B is equal to negative 2 dot plus 15 times rand n. So there's an n on the end because it's a normal distribution, 10 by 7. So this is saying give me 10 by 7 standard normal. Then I'm going to give it a standard deviation of 15 and then shift it to the left by 2. Or I can do rand normal, negative 2, 15, 10, 7. And then for indexing, we want to grab the first 5 rows and first 5 columns of A, and then the first 5 rows and last 2 columns of B. And we're going to call that C. So the way we build matrices in Julia is with brackets. So this bracket says I'm instantiating a new matrix or array. And then I'm going to say 1 to 5, comma 1 to 5. And then B of 1 to 5, comma end minus 1 to end. So end is a special word in Julia that means the last one. So the second to last and the last is what this end minus 1 to end means. And then lastly, we want to do a bit array or dummy variable. So we want to grab just the non-positive elements from A and keep those and then replace the positive elements with 0. So I'm going to do A dot times A of A. Well, sorry, I'm just going to do A dot times A dot less than equal to 0. And if we push play, we can run all these things. And then if we open the Julia extension, then it's going to have these objects on here. So it's going to have packages we loaded and elements that we've created. I'm going to delete these print line statements here. All right, so that was part A. And then in part B, we want to get comfortable with size of arrays and how many elements they have. So if I want to know how big an array is, I can do size. I can do size in each dimension. So the comma 1 and comma 2 is first versus second dimension. I can do length, and I can do the colon within the brackets. So that's going to convert A to a vector. And if I do all these, they're all going to tell me 70 or 70 by 1 in some form or another, as you can just see here. So a lot of this stuff is just like building vocabulary in a foreign language. You just have to kind of memorize it. There's no real way around it. All right, part C is going to have us get the number of unique elements. So I can see what's the total length of my matrix D, and then what's the length of the unique elements that have been filtered out. So if I run that, then I'm going to see that 28 elements are unique out of 70 total. So there were a lot of zeros in D. And then if we press on to part D, now we want to do something called reshape. Reshape is how we can convert the size or the shape of an array into different configurations. So I had a 5 by 7 or a 10 by 7 array. I can reshape that into a 70 by 1 vector or a 1 by 70 vector, or probably those are the only ones because 7 is a prime number. But we could think of other configurations to do as well. I guess we could do a 35 by 2 because it would still be 70 elements. So how do we reshape? So we take E is going to be the new thing that we want to create, and then equals is how we assign the calculation after the equals back to the thing that we want to name it. So we're going to reshape B into a 70 by 1 vector. And there's a bunch of different ways that we could do this. The easiest way is to use the colon operator. But we could do 70, comma 1 in parentheses. We could do, if we didn't know what the length of B was, we could just put it like that. Or we could do size of B1 times size of B2. So these are all equivalent ways to get that reshape done. And then part E is asking about 3D arrays. So I have a function in Julia called cat. So I can take A and B and concatenate them in the third dimension. So if we just look at what this is down below, we've got a 10 by 7 by 2 array. So now we have a 3-dimensional array. And the first dimension is a 10 by 7 2-dimensional array, and the second element of the third dimension is another 10 by 7 2-dimensional array. So we have like a Rubik's Cube going on that's a 10 by 7 by 2. And why would we want to have this? Well, there's a lot of applications where we might want to be able to store numbers in more than just 2 dimensions. And this is how we would do that. All right, so now we've got part F, where we're going to reshape in 3D. So here we call it permute dims. and we're going to give it D, and then we're going to give it a comma separated list of how we want the dimensions to be permuted. So this is like taking a Rubik's Cube and rotating it so that instead of having the white side face you, now the white side is facing up. And so if we do this, I meant to put an F here. Then we're going to have the 2 by 10 by 7 that the PDF asked for. Part G has to do with Kronecker products. And we want to do G is equal to Kron of B comma C. So the Kronecker product is a matrix algebra operator that can sometimes be useful for expressing econometric estimators in terms of matrix algebraic operations. And one thing that it can't do is operate on a three-dimensional array. So the Kronecker product is only defined for two-dimensional arrays. So if we try to do it on three-dimensional arrays, it's going to give us an error. And it's going to tell us that I can't do this on a three-dimensional array. So that's how that works. Now let's do a little bit of input-output. So how do we save our work in Julia? So we're going to use the save function, and we'll call it matrix practice.jld. And then we're going to give it a list of names and objects. And this list is not going to be very creative, but it is going to be sufficient for what we want to do. And if we hit save there, it's just going to save it. I guess I don't have. Oh, I guess I didn't run the code for E. That's what the deal is. So if I say E is equal to B of colon, and then I rerun it, and then G I didn't do in. All right. Well, that's going to run just fine once we kind of run everything top to bottom. And then part I is just saying, well, we can do any subset of this that we want. So we can grab the same thing here. I can call it first matrix, and then I can just do A through D. So why don't we run this so far, just to verify that the code runs. And it looks like it ran because it didn't really show anything. So it didn't give us a new error. We can hit Control L and just to kind of clear things up and rerun it if we're worried about it. But it looks like everything's there. And we have over here in our workspace, we have G and E and all those things. Let's take a break and then I'll come back for part 2 shortly. Now the last thing we'll do is look at how to export to CSV, which is a very common data format. And then at the very end, we'll see how a function works and how we can call that function to streamline our computation. Part J asks us to export the matrix C as a CSV. And here we're going to use a function called csv.write, and then we give it the file name that we want it to be called. And then the trick here is that we have to actually convert it to a data frame and then save it to the CSV. So this file should save a CSV in the present working directory, and we could specify an alternative file path in the file name if we wanted to save it somewhere else. And we can also do this with a tab delimited. So I could call this .dat and then say delim equal \t. And this is part K is asking for us to do that with matrix D. And we could do that. And now we have a tab delimited one instead of a comma delimited. And sometimes that might be more useful. I also wanted to kind of show you what's called piping. So an equivalent expression as line 90 is to use Julia's piping. So this vertical bar with the greater than sign is the pipe. And then this arrow is saying pass what came after the pipe or what got piped in into the next function at the argument x. And then we're going to do the same thing here with the csv.write. And this is the exact same code as what we just had. And you might think, well, that's uglier. It took longer. Why would we want to do that? Sometimes it's easier to break out the nested computation into a single chain. So this says take D, make it a data frame, write it to the CSV with this name. So sometimes it's easier to understand that way, but I prefer to just have a lot of nested parentheses, but people have different preferences. So the point is that Julia can accommodate a lot of different preferences. Now, if you have the PDF open, the very last thing that it asks for is to write a function that wraps around everything and returns A, B, C, and D. So this is one of the most important tools of using Julia is to write a function. So we write function Q1. It has no inputs because it's just generating data, so it doesn't need any inputs necessarily. And then we do the return, A, B, C, D, and then we write end. So that's how we do the function. So everything inside the code is in a function. And I'm going to indent this, since that's standard practice for clean coding, is to know where your functions begin and end. And then we can call this, we can say A tilde, B tilde, C tilde, D tilde equals Q1. And that's how we would generate this data. So if I sort of re-clear the output in the bottom terminal and push play, I need to save the file first. So that is something that we should do periodically. And then you'll see here in the workspace, I now have D tilde, C tilde, B tilde, A tilde as outputs. So that is how we do functional programming with Julia. And the reason that functions are so important in Julia is because that's how the compiler speeds up our code. And stuff that is not in a function, it's very difficult for the just-in-time compiler to speed it up. So that is a little bit about how to get started in Julia. I hope you found this helpful, and you can now proceed with question 2 on your own and see if you can figure out some of those questions.